use another phosphate. It goes into the molecule. So we're using up 2 ATPs, okay? And we get this molecule, fructose 1,6 phosphate. And then that falls apart. And we get 2 3-carbon molecules, and then that's converted to that. We get 2 glycerol diphosphate. Then we make NADH. That's a redox reaction. And the next step is the kinase also can make ATP. In the first part of it, we used ATP. But now we're going to make ATP. That's what a kinase does too. Okay, so here we're going to get 2 ATPs. That's what a kinase does. So we put 2 in the beginning, and now we have 2 here. So as far as the ATPs, it's 0. We put 2 in, 2 out, but we have the later useful with it. And then some other stuff happens here, and you come to the end here, and the last step is that a kinase is going to work again, right? Makes 2 ATPs. Those are the 2 net ATPs of glycolysis. And that's made through substrate level phosphorylation. No, just enzymes and substrates, no membranes or anything. So these 2 ATPs are made by substrate level phosphorylation. And you get 2 pyruvates. And the pyruvates enter the mitochondrion. All this is going on in the cytosol of your cell. Cytosol. All the enzymes are soluble, easy to purify, and all that kind of stuff. And then we take pyruvate and bring it into the mitochondrion, and we make acetyl-CoA. So that's the next step. All right, there's our pyruvate from glycolysis. It enters the mitochondrion. You're going to need some energy to get pyruvate into the mitochondria. You might want to think about that. Where's that energy coming from? It just says a transport protein, not true. There's much more going on here. It involves photomotor force. So we make NADH and we make acetyl-CoA. And that begins the Krebs cycle. Now the Krebs cycle is more complicated than glycolysis. So they don't even give you the names of the enzymes anymore. That's not scary. So overall, in the Krebs cycle, this figure, 9.11, summarizes what's happening. The acetyl group has got 2 carbons. The acetyl group has 2 carbons. Okay? There it is, the 2 carbons of the acetyl group. That's got energy. And we want to extract the energy from that acetyl group. That's the purpose of the Krebs cycle. And as those 2 carbons go through the Krebs cycle, you make 3 products. You make 3 NADHs. There they are, black and white, well actually yellow and white. 3 NADHs, an ATP. That ATP is made through substrate level phosphorylation, and then an FADH2. So those are the 3 products of the Krebs cycle. If you can remember that much, you're all set. Krebs cycle, 3 NADHs, 1 ATP, 1 FADH2. So the energy that was in glucose is now trapped in those compounds. Glucose is gone. It's gone out for CO2 and water. It's gone. But the energy that was in glucose is now stored in NADHs, the 3 NADHs, the FADH2, and the ATP. Yes.
What happens is CO2 not producing?
Sorry?
CO2 not producing the cycle.
I can't hear you. It's loud.
Is CO2 not produced in the?
Yes, CO2 is produced in the Krebs cycle.
So it's not one of the next things that are.
No. When you go from pyruvate to acetyl-CoA, you use 1. The acetyl group has 2 carbons. They are formed as 2 CO2. So the carbons are all gone. Okay. Remember, everything was times 2, so it's actually 6. Okay. Any questions about the Krebs cycle? Let's lock this down.
I have a question.
Yes.
For the things produced in Krebs cycle, is this per glucose molecule or?
We're going through a series of steps.
Yeah.
So when we went through glycolysis, we extracted out a little energy. Okay? We extracted out a little energy. We made two ATPs and we made two NADHs. But most of the energy is still in the molecule. So now it goes from pyruvate to acetylcholine in the Krebs cycle, and you lose one of the carbons of CO2 times 2. Okay, and 2 carbons are left over, and they're tied into coenzyme A. And you have what's called acetyl-CoA. And that enters the Krebs cycle right here, and it goes through. Each acetyl-CoA goes through, and the products that are formed are 3 NADHs, 2 CO2s, 1 ATP, and 1 ADH2. That's the thing you should look at. Figure 9.11. That'll tell you the whole story. Yes.
Yeah, but what I'm saying is this like for every pyruvate or like
Each pyruvate is converted to acetyl-CoA, and then it's Krebs cycle. It burns up the CO2.
okay, so if glucose makes 2 pyruvate, then it's gonna be double of this, right?
Yes, that's
Okay.
true. Yes.
Can you explain what energy is used to bring pyruvate to mitochondria?
What?
Can you explain like what energy is used to bring pyruvate to the
Well, you know, it's a charged species. Okay? I would read the text. It's in there. I'm going to leave that for you, because I know you'll enjoy finding the answer. Mean answer, huh? Okay, so as we go through the Krebs cycle enzymes, I mean, I know this is hard, because the organic chemistry is worse than what we had in glycolysis, which is actually childish. So, as we go through the individual steps, the first thing is, this is figure 9.12. So the acetyl-CoA binds to oxalic acetate, and you make citrate. It's got 3 carboxylic acids, right? Can you see that? 3 carboxylic acids. Then, what happens is, an OH moves around from one position to another. You get isocitrate. And then in 2 successive steps, you make NADH, you lose CO2. 2 successive steps. Okay? Over here now, you have a compound whereby you make another NADH. So here's 1 NADH, 1 CO2, second NADH, second CO2. Over here, we have this high energy compound called acetyl-CoA, and there's a lot of stuff going on here, but we're not interested in all that. When this bond is broken, there's enough energy produced to make 1 ATP. This is substrate level phosphorylation. This is the only part of the Krebs cycle where you make an ATP through substrate level phosphorylation. You might want to know that. You might want to know that. Okay, then it goes on, and you make FADH2. Okay? And then there's some more fooling around, and you make another NADH at the end. So 1 acetyl-CoA goes through the Krebs cycle, and it makes 3 NADHs, 1 ATP through substrate level phosphorylation, and 1 FADH2. So the next thing now is how to extract some energy from NADH and FADH2. Okay? That's the next thing. That involves 2 components. The first component is the electron transport chain. The electron transport chain, figure 9.13. What's the big deal here? The big deal here is NADH has about 53,000 calories. And when it reacts with oxygen, it's going to release that 53,000 calories. Okay? So when you go from NADH to coenzyme Q, everything in here are electron or proton carriers. So you have iron in complex 1, you have iron in the cytochromes, you have iron in the cytochromes, and in this enzyme called cytochrome oxidase, you have iron and copper. So it's like an electric wire. The electrons are going through oxidizing and reducing, and as they go from NADH to Q, you release 17,000 calories and make an ATP. You go from Q to C, cytochrome C, you release another 17,000 calories. That makes the second ATP. It makes the energy available to make a second ATP. And then from C to oxygen, another 17,000 calories. That provides the energy to make the third ATP. How does that happen? That's called chemiosmosis. This is the main figure that you should be familiar with as far as how oxygen phosphorylation works. This is it. So here we go, it's just arranged now in a linear way this way instead of this way. So what do we got here? We have complex 1.